Hello, my name is James Ruiz, and this is my final project presentation. So the main goal of this project was to build a tool that evaluates the draft value of NFL players based on real performance data, and this data is taken from an external library that is connected to several APIs from the NFL API, and we use that to compute a value that reflects each player's kind of contribution. And this project was designed in mind to suit any fantasy football enthusiasts who want a more data-driven view of player management and performance. So I wanted to do this by designing a draft value score generator, and we processed the player stats such as total rushing yards, total receiving yards, touchdowns, points per reception, and because each stat is weighted, we're able to compute an average per game that makes scores comparable. And this is a metric that is used as a foundation for our system. Then once we have the scores, we can give the client more control of which players to focus on. So the user selects any player, which serves as the benchmark, and then also defines a plus minus deviation range, so maybe plus minus 5 points, and then it filters all the players who fall in that range, and it gives us a more comparable group as opposed to a larger data set. Then once we have that, we're able to construct the trees. So the goal was just to build 2 trees, a self-balancing AVL tree that is rooted at the specific player, and then the goal in mind was to have O log n performance for search and insertion and provide constant rebalancing after said operations. Then after we implement the B tree, which is good for wide data sets, and just have correct functionalities of splitting nodes and still maintaining balance while keeping the height at as minimal as possible. And then also just test both trees for efficiency and just measure which data structure has more optimal performance. So an AVL tree is a type of binary search tree, and a binary search tree just means that it can have up to 2 children, one on the left and one on the right. And a key property of just binary search trees, as we learned early in the course, is that the left children must have smaller node values while the right children must have larger values than the parent node. And also we learned that AVL trees differ from regular binary search trees in that they automatically rebalance themselves after operations of insertion and deletion to prevent skewed trees. And this is done by maintaining a balance factor, which is computed based on the difference in height between the left and right subtrees. And an important thing to note is that the balance factor must stay within the range of -1 and 1 for every node. So what would we do when the node's balance factor goes out of balance? We would then apply one of the 4 types of rotations in order to rebalance the tree. And I will get into that into the next slide as an example. But overall, these are just structural changes in order to uphold the properties of binary search trees and remain balanced. So what is the big O for average and worst case for AVL trees? Because of balancing, it's consistent across all operations. So it is just logarithmic O log of n. And it just goes to show that it is a good choice when using dynamic data sets. So here's an example of rotation. We have our initial insertion order at the top, and this is the structure before rebalancing. So as we can see, Josh Allen is a root with a left-heavy child, and that left-heavy child has a right-heavy subtree. So looking at the balance factors for each, we see that we have a balance factor of -1 and +2, which infers that we need to do a left rotation on this node. So after that left rotation on this node right here, this is supposed to be an arrow point upwards, but we look at the structure and it is more like a linked list. And computing the balance factors for each, we also have Josh Allen's balance factor is +2, which does not fall in the range of -1 to 1. So that means that we must do a right rotation on this node. So after that right rotation, the tree is now balanced, And looking at each balance factor, they all fall within the range of -1 to 1. And this is just an example of left-right rotation. And it is used when the node's left child is heavy on the right. And we just rotate left and then rotate right on the unbalanced node to achieve balance. So moving on to B trees. B trees are also a type of binary search tree, but they are optimized for systems that handle large chunks of data. And an example of this would be such as file systems. It is a multi-way search tree. So basically it means that unlike regular binary trees, they have 2 children per node, but then B trees are different in that each node can have more than 2 children. They are also self-balancing, like AVL trees, but they handle balance in a different way. Instead of rotations, they split nodes when the nodes become too full, and it overall keeps the tree shallow, which reduces the number of input operations when we insert or search for an element. So all the leaves appear on the same level, which overall just helps to maintain balance. And the internal nodes have T to 2T children, and T is the minimum degree and defines how many children a node can have. So nodes can hold multiple elements, going back to how it is a multi-way search tree. So they can store up to 2T minus 1 keys or elements, and it just shows why it is more preferred in larger data sets, because fewer nodes are needed and we can store more data per node. So looking at the average and worst case behavior and time complexities, they also offer logarithmic performance for all the operations like AVL trees, so it's O log n. And yeah, here's an example of the theory behind B tree. So if our B tree has a minimum degree of T equals 3, each node can hold up to T minus 1 or 5 elements and have up to 2T or 6 children. So we have a list of players. They are randomized and they are not in order based on score or anything. And so since the node capacity is 5, we would safely insert the first 5 values into the root node. And the values aren't shown for simplicity's sake, but just pretend that we sort this insertion into the node. So this is a little bit faulty, but when should be after Allen if it was based on score, but just for simplicity's sake, we'll keep it as is. So when we try to insert the next player, which is Tyreek Hill, the node already has 5 elements, so it is already at its max capacity, and trying to insert a new element into the node would ultimately trigger a split. So the B tree would handle this overflow by splitting the node around the middle element, and as I said earlier, whence should actually be after Williams if it was score, but I think the way I did it without putting the score in made it harder to visualize. But we assume that once is the median and is at index 3 in the list, so that is the median that will be promoted to the new root, as you can see. And the remaining values are split into 2 child nodes, so we have St. Brown and Allen on the left, and then Williams, McCaffrey, and Hill on the right. So this is what the B tree looks like, and it's still within capacity. The amount of children is less than 6, and the amount of elements in each node is less than 5. So this is our final sorted list, and we continue to insert the rest of our players, Jefferson and Lamb. And doing so, Jefferson would be placed into the left child, and Lamb would be in the right child in terms of scoring. And it is still B tree compliant as well. So here are my project resources. I referenced the assignment 5 implementation to create the modeling for the BST and AVL node entry classes, and I integrate bits and pieces from that into mine, but had to change some things within to suit the scope of the project. And my data source was the NFL Data Pi library, which is a good tool for importing the NFL player statistics into Python. And we use that structured data to calculate draft value scores and populate our tree structures. So here is how I imported and acquired the data, as well as inspected it and did some pre-processing on it as well. So I did this by creating a function that imports seasonal data for the 2023 NFL season using the NFL Data Pi library. This function overall just pulls the player statistics and metadata, such as the names and IDs, so that we can link the raw stats to the names of the players. And I also did some light pre-processing to rename the columns just so it's easier just to reference. And from there, we were able to construct the draft value scores. And at the bottom is just examples of stat columns and the metadata. So it just helped me understand the overall data schema and showed what raw features I was dealing with from this library. So once I had the full data frame from the NFL API, I extracted the relevant columns for fantasy scoring. So it would be things like points per reception, receiving yards, receiving touchdowns, etc. And before going on, I wanted to check if all the expected columns were actually present in the NFL data frame using a for loop, and then I raised the key error if anything was missing, and that was just for validation. Then the NFL Data Pi has a lot of libraries under the hood, such as pandas, so I used Dropna to filter out any rows that were missing any player names or fantasy points, since those are kind of necessary components in order to compute a draft value score. Then I used iteros to loop through the data frame and build a result list. And in each row, I extracted the stats into a dictionary, which is paired with the player's name in order to create the tuple. And the end result is just a clean list of tuples with the first element of the tuple being the player name and a corresponding dictionary with key value pairs being the stats and the values. And that would just be used to create the draft value score later on, as I will depict.
So to calculate the draft value score, I wrote a function calculate DVS, and the idea was just to take the key offensive stats such as PPR, receiving yards, and touchdowns, and rushing stats, and put them into a weighted formula that reflects the fantasy value. So each stat is pulled from the dictionary using .get to avoid the key errors, and if a stat is missing, I would default it to 0. But for the games, I would default it to 1 in order to avoid division by 0 errors. So the scoring weights, such as 0.5 for PPR and 2 for touchdowns, are just based on standard fantasy football rules, but they can easily be altered to one's liking. And I take the sum of that and divide the score. I take the sum of the score and divide it by the number of games played to normalize across the players who have played different numbers of games. And it is integrated into my main function through a for loop, and we will later implement that into our tree construction. So this BST node class for my player leaderboard builds on my assignment 5 BST node class, and the differences are that it is more specialized in that it is designed to store a player's name and their computed score, or the draft value score. Like before, it initializes left and right pointers, but I also add a deleted flag in case I want to support or mark nodes without like having to remove them physically. So in the starter code for assignment 5, normal and order traversal was already implemented, and It essentially walks the tree by visiting the left node, then root node, then right node, and then returns an ascending order of values. But for my project, in order to build the leaderboard where we have the top scores first, I essentially flip that logic and would use reverse in order traversal. So it would visit the right node, then the root node, then the left node, and it would just return a descending order. So how it basically works is that we initialize the empty list to store the output, and the entries would be the name and the score. And then we have our recursive helper function, private method traverse. And first we'd recurse onto the right subtree with node.right. And since the higher score is on the right side of the tree, the higher scoring players are visited first. Then we check if if it's not node.deleted. So if the node is not marked as deleted, we would append the tuple name score to our result list, and it just ensures that players that are deleted are not on the leaderboard. Then we recurse onto the left subtree, which has the lower range of scores, and then we would complete this reverse in order from right to node to the root to the left, and basically it is just called on the root of the tree, and then once the result list is fully populated, we return it. Then the get top players method essentially just slices the list to return the first 5 players, since we already sorted it efficiently in the function above. The AVL node class is generally the same as assignment 5 almost in its entirety, except for the fact that it is more designed to store name score for the scope of the project as opposed to generic data. So it would just the way that we're storing data for our nodes is different. But going through it quickly, it inherits from BST node, so it has the basic functionalities like the left right child pointers. And then we would add an extra attribute, height, and then we initialize it to 0, so that the bounce factor can be easily found. Or yeah, and then we have our height. We have the getter and setter methods for the height, and then we have the define child heights function, which returns the heights of the left and right children. So we just check if a child exists in our node, then we would get its height, and if it's a leaf and it has no children, then we would treat it as -1, and then we'd find the left and right heights and then return it. Then we have the adjust height method, which kind of updates the node height after insertion or deletion operations. So it would call the child heights, it would take the max of the 2 child heights and then add 1 for the current node. And it's just an essential method for whenever the tree is modified, because the entirety of balancing and the logic behind it depends on the current heights being accurate. So for our current AVL tree class, we start by inheriting it from leaderboard BST, meaning that it would be able to handle the additional methods that we implemented, such as get top players and get top players in range. Then we have a property method, height, that checks if the tree has a root and returns the root's height if it exists. If not, then we return -1. And then we have our private insert method, which starts off with the base case. And the base case, once again, is just checking if the node is none or empty. And then if not, or if it is, then we would just create a new AVL tree node with the name and the score. And then we have our conditional, which basically compares the new node with the one that we want to insert with the current node, and then it decides whether or not we go left or right, or whether we go left or right. So the first condition is we check if the score is greater than node.score. So if the score is greater, then we go right because the higher values are on the right side of the tree. Then if the scores are the same, then we just break the tie by checking which name comes first alphabetically, and that just ensures that there are no duplicates. And then in all other cases, then we would just go left if the score is less. And this ultimately just keeps the tree balanced and sorted. And then we have our public insert method, which calls the private insert method on the root. So when dealing with rotations for the AVL tree, we have a rotate left and rotate right. So we do a left rotation when the right subtree of the node is heavier, so then it's right imbalance. Then right rotation when the left subtree is heavier, so it would be left. And then the way it would work is for rotate left, it would store the right child of the node, then reassign the right pointer to right dot left, and then it would make the current node the left child of the first right child, and then we just update the heights on both of the nodes using adjust height, and then it would just return the new subtree, the root of the subtree, sorry. And the same logic basically happens to rotate right, it would just be inverted. And then for rotate and fix height, that would just handle the double rotation cases like left right and right left. So it checks if the balance factor is greater than 1, so that would mean it's left heavy. And if it is, then it checks if it's a left right case. Then it would just perform a double rotation if it's needed. So it would be a left rotation, then a right rotation succeeding that. And it would also, and the same way it would handle right left cases by just checking the child heights of R in this case, or the right node. And then we have a is balance method, which is just for debugging purposes, and it walks the tree using recursion and would just print out unbalanced nodes. So for our AVL tree search methods, we start with the private method. So it is basically a recursive binary search. So we start with the base case. If the node is none and it's a leaf, then we just return none. Then if that doesn't apply, then we check if the scores are the same. So if the scores are the same and the names are the same, and I use the built-in methods .lower and .strip for accessibility, we would return the node. And then the second conditional is just checking for ordering. So if the score is lower, then we go left. And then if the score is equal, but then the name is alphabetically less, then we go left. And then if none of the conditions apply above, then we would just search right. Then that private method is just called the public method, and it just does the recursive search from the root. Moving on to the B tree node class, it represents the single node in the B tree. So we first start with a class variable min degree, which is the minimum degree t of the B tree, and we set that to 2, and the max number of keys would be 2t minus 1, so it would be max 3 keys per node, and then the max number of children would be 2t, so that's 4 children. So for dunder init, we would have the self.t equals t, so that just stores the minimum degree t for the node, and then we have a boolean flag for our leaf parameter, and it would raise true if the node is a leaf node, so it would have no children, and that's just important for insertion, because if the node is just if the node is a leaf, then we would just insert it into the keys. And then self.keys is a list of the name score tuples, and then self.children is a list of the children objects of the nodes, and then we have our thunderstring method. Now we have our B tree structure class. So we have, once again, our class variable min degree. Then in our dunder init constructor, we would have self.root equals B tree node, and then we'd pass in the min degree t, and then set leaf to true. So that means that it would just start off as a leaf node because it's the only node at the start, and that line just initializes just the root node. And then we have self.t equals t, which stores the min degree parameter, so it can be used during operations like insertion and the splitting of the nodes once we reach overflow. If we want to use the insert btree method, then we need to define a new method, insert on full, and that just handles all the cases where the btree node is guaranteed not to be full, so has fewer than t-1 keys. So it's called recursively, so from top to bottom throughout the tree, and then it just inserts the key in the right position. So we just check if the node is a leaf, then we append that to the keys, then shift the keys, and then insert the key into the right position. And then we find the child that would receive the key by comparing the scores, and then check if the child is full. And then if it is full, then we split it using split child, which I will get into after the slide. And then after splitting, then we would see again if we should go right or stay on the same, and then recurse onto the correct child. So this is also O log n because of the tree heights, and this maintains tree balance and order functionalities. So then that is just used in our regular insert. So insert not full is used in our insert method. So we start off by creating a reference to the current root node, and that is helpful just in case that we need to replace the root once it becomes full. And then we check if the length of root keys is equal to 2t minus 1. And if that is true, then we must split the node before inserting another key, or else the tree would not be balanced. So if the root is full, then we would just create a new root and then set the leaf to false because it is no longer a leaf, and it will have I think it would be the old root, would be the child. And then new root.children.append just makes the current root the child of the new root, and then we call split child on self, which splits it, and then the middle key is moved up to the new root, and it is split into two nodes. But I will get into that in the next slide. And then we call insert non-full because the new root is not full, so then we can safely insert the key using that helping method. And then we update the root pointer to the new root. And then if it's not full, then we just insert it into the root node using insert not full. And nothing's really changed here because there's space to insert a new key. So our split child method splits the full child node, which would be x.parentChild at index I into two nodes. So the left half would stay in the current child, which would be x, then the right half is moved to the new node, which would be y, and then the middle key would be the new parent. And this split child method is important because it keeps the tree height small and also prevents having an overflow of keys in one node. For our B-tree search, we would check if there would be no node on the first call, and then we would just start from the first node, or the root node, sorry. And then for our main loop, we just iterate over the keys in the current node, and then compare the score to the scores in each of the keys, and then we would stop that loop when I reaches the end, or we find a score that is greater than or equal to the target. And then this loop ultimately finds the position, which is I, where there would be a match or where the current child would be located. And then we have another condition that checks if the key at index I is a score that equal to the target, and then that would be returned. And then lastly, we would just check if we're in the leaf node, and then there's no match, then the key's not in the tree, and then we can't recursively search anymore. And if we still haven't found the key, then we just recursively search the child at index I. So now I begin to set up the testing environment using unit tests. So to set it up, I created a list of tree sizes that I would use to evaluate the performance of my trees. And then it would just be called before each test case just to reset. And then it's just representative of small, medium, and large data sets. So then for the data generator, there are not enough NFL players to cover all these input sizes. So for name, I randomized a 5-letter string, and then for score, it would just be a random integer between 1 and 10,000. So for our test cases, I tested the insertion performance and search performance. For insertion performance, we compare the time that it takes to insert the name score tuple pairs into the AVL tree versus the B tree across the sizes that we define. So for each size and self.sizes, we would generate the data, and then time is measured using time library, time.time function, and then the results are printed to see which tree handles the bulk insertions more rapidly. And then for the second test search performance, we would see how quickly a tree can perform the repeated searches. And the way I did this is I filled both of the trees with the same data, and then the last element is used as the search target, and then each tree performs 1,000 search operations, and then we calculate time using time.perfect counter, and then we print the results. Test B tree consistently performed faster for both operations across all the input sizes. Talking about insertion, the input size for the large dataset, 10,000, it took about more than 2 times longer for AVL tree than B tree, and I think this is because the structure of B trees are more shallow and the height is minimized, so that just reduces the number of insert steps that we have to do. But in contrast, the AVL trees, like, they have to rebalance after every insertion, and especially when the tree is skewed, we sometimes have to perform some single or even double rotations, which adds more overhead and just more recursive steps when adjusting the heights. But it's safe to say that they're both logarithmic, but they do have some differing constant factors where the frequent rebalancing of AVL trees kind of slows down the runtime. And for search, B tree was also faster. AVL tree did win one search time test, which was the middle input size, but I think AVL trees, they just have too much depth, and having to traverse through such a large tree would take much longer as opposed to a shallow tree. That is my conclusion for it. But overall, the time complexities are both O log n, but just the way each operation works through each tree, B trees are much more efficient in terms of larger data sets.
So here's my main.py file. Because my presentation has already been pretty long, I will try to keep this short, but basically it encompasses the whole program, and we first import all our files plus the fantasy data, and then on the client side, we just basically ask the user if they want a B tree, AVL tree, using point choices, and then based on their choice, it runs the appropriate model, the B tree mode or run AVL mode, and then it also prints top players within the range of 14 and 22 based on the scoring. So that's just all the top scoring players in the NFL, and it would ask for a player of choice, and then it would ask for a player of choice to center around whichever tree, either the B tree or AVL tree, and then generate that tree, check the tree balance, and then also calls for insertion after, and then reprint the tree. So I will show you how it works right now. So say we want to create a B tree. We'll say Jalen Hurts. We'll say 0.5. And here we can see a mini B tree around Jalen Hurts, and it is B tree compliant. And then if we want to insert a new player, and adds the key to this node.
Now I will demo the AVL. So say 2, we will do the same. So 5, use the AVL tree. It looks compliant and verifies the helper function that it is AVL balanced. Now we'll try insertion. And since it is the lowest score, it should be right here at the leftmost subtree child.